Hello YouTube, welcome to a lecture about Henderson-Hasselbalch equation. In this lecture I will describe the Henderson-Hasselbalch equation as well as the correlation that it has with the biological bicarbonate buffering system. The Henderson-Hasselbalch equation describes the pH as a measure of acidity in biological systems. In an aqueous solution, such as our blood, or extracellular or intracellular fluid, there is a weak acid, for example this generic acid, which dissociates in proton or hydrogen cation plus this conjugated base of the previous acid. This reaction is in equilibrium. It means that the concentrations of the generic acid, of the conjugated base, and of the protons either do not change over time, or they change under the presence of another acid or another base in the biological system, but the pH of the solution remains the same, or there is a minimal change of pH with minimal importance. There is an equilibrium constant Ka, which is determined by the concentrations of each aqueous particles of the previous reaction. This constant is called acid dissociation constant, or Ka, and expresses the qualitative measure of the strength of the acid in the solution. It is equal with the concentration of hydrogen cations, which are the protons, multiplied by the concentration of conjugated base of the acid, divided by the concentration of the weak acid. In practice, we use the logarithm to base 10 of this constant, the log to base 10 Ka, or more simply log Ka. I will explain some basic logarithmic rules in order to understand the mathematical approach of this lesson. At first, what is a logarithm? Logarithm is a number. For instance, the logarithm to base 10 of 100, or more simple, log 100 is 2, because 10 in the power of 2 is equal with 100. A very good graphic in my mind that I have made, good for remembering this basic logarithmic rule, is that from this equation, the log goes away from the left part, the 10 goes under the equal symbol to the other side, and becomes bigger as well, and the 2 becomes smaller, and becomes the power of 10. In my opinion, is a good way to remember the most important rule of logarithms. Now let's mention some more simple but important rules. The log to base x of a multiplied by b, when we have a number like a logarithm that is like this, that logarithm to base x of a multiplication, I mean this x is a variable, and these two can be any kind of numbers. So this is equal with the logarithm to base x of the first number, in this case the number a, plus the logarithm to base x of the number b. In the next case, when we have a logarithm, to base x of a division, such as here, of a number divided by another number, this is equal of the logarithm to base x of the first number minus the logarithm to base x of the second number. As well over here, when we have this is equal with b multiplied by log to base x of a, like this. It's a multiplication, so let's write it better over here. When we have log to base x of a in the power of b, that is equal with b multiplied by logarithm to base x of a, and the last one is ex, that x can be any kind of number. It is equal with minus logarithm minus log to base 10 of whatever number it can be, the x. Or it is equal to minus log, because whenever we see a logarithm to base 10 of a number, that is equal with just log of this number. We have over here the Ka, the acid dissociation constant, which is this, that is equal with the concentration of the hydrogen cations multiplied by the concentration of the conjugated base of the weak acid, and that is divided by the concentration of the weak acid. Now this is equivalent that log to base 10 of Ka, it is equal with a log to base 10 of this. But as can we see over here, we see a division which is like this. We have green A multiplied by B divided by C. In this case, the A represents the concentration of hydrogen cations, the B represents the concentration of the conjugated base of the weak acid, and C represents the concentration of the weak acid. But whenever we have something like this, this is equal with A multiplied by B, which is divided by C. So we will go on. We're gonna replace this according to this over here. So this is equivalent with log to base 10 of Ka, that is equal with log to base 10 of this, so log to base 10 of hydrogen cation, the concentration, multiplied by this division of concentration of the conjugated base divided by the concentration of the weak acid. But now we will use one of the features which we saw in a previous slide. Actually, as we said before, when we have a logarithm like this and of two numbers of actually that are multiplied each other, we can write log of the log to base x of the first plus log to base x of the second. In this case, the A is the concentration of hydrogen cations, whereas B is the concentration of the conjugated base of the weak acid divided by the concentration of the weak acid. So this is equivalent that log to base 10 of Ka, it is equal with log to base 10 of hydrogen cation plus the log to base 10 of this. Now we're gonna use another feature that we have described earlier. When we have, as we mentioned before, dx, that x can be any kind of number, but that is equal with minus log to base 10 of the number that we had over here. This is equivalent that minus px is equal with log of x. And this we are gonna use in this case. The log to base 10 of Ka, it is equal with minus pKa. This is equal. Now we go to the second part. The log to base 10 of the hydrogen cations, of the concentration of the hydrogen cation, is equal with minus pH, and the rest is the same. Now we are gonna add pKa plus pH in both sides. So plus pKa plus pH minus pKa, it is equal with plus pKa plus pH minus pH and the rest. And over here we can make some simplifications. For instance, the plus pKa we just remove with the minus pKa. They are simplified, and from the second part of the equation, the plus pH with the minus pH, and now we have the equation of Henderson-Hasselbalch. So, but in the next slide, I'm gonna write it better. So, this is equivalent, of course, with the equation of Henderson-Hasselbalch. We can use the Henderson-Hasselbalch equation to relate the pH of blood to constituents of the bicarbonate buffering system. There is this equation of Henderson-Hasselbalch. This is the logarithm of the acid dissociation constant of carbonic acid. It is equal to 6.1. So this is the concentration of bicarbonate in the blood, and this is the concentration of carbonic acid in the blood, and there is another equation which we're going to use. It's this one. The concentration of carbonic acid in the blood, it is equal with the Henry-Law constant, which is equal with 0.0307 multiplied by the partial pressure of carbon dioxide in the blood. By combining these two equations, this implies that pH is equal, we write the logarithm of the acid dissociation constant, which is equal to 6.1 plus and this. So we write it. No, but the concentration of the carbonic acid, as we mentioned before, is equal with this. So instead of writing just with the brackets the carbonic acid concentration, we're gonna write this over here. So the Henry-Law constant is 0,0307 multiplied by the partial pressure of carbon dioxide, and this is the final Henderson-Hasselbalch equation that describes the pH as a measure of acidity in our blood. The concentration of carbonic acid in the blood denotes metabolic disease in the blood. When there is, whenever this concentration is high, that denotes metabolic alkalosis, whereas whenever is low, below the normal range, that denotes that's metabolic acidosis. So the partial pressure of carbon dioxide in the blood denotes respiratory problems, and whenever there is high partial pressure of carbon dioxide in the blood, we have respiratory acidosis, or whenever there is low uh, partial pressure of carbon dioxide in the blood, we have this denotes actually respiratory alkalosis. Thanks so much for your attention, and if this video was quite helpful for you, thumbs up and please subscribe. Thanks so much.